Hey everyone, welcome back to our channel. Today we've got something special lined up for you, a series that's perfect for all you newcomers out there. We're diving into the world of Docker, and trust us, we're going to make it easy for you. So what are we going to cover in this series? Well, we'll be breaking down Docker from the ground up. We will be talking about containers, images, Docker files, and all of the essential components you will need to know. Whether you're a developer, a system administrator, or just someone curious about containers, this series is for you. If you're new here, please make sure to hit that subscribe button to stay tuned for more in-depth tech content. Before we get into the nitty-gritty of Docker, let's journey back in time and explore three common approaches to deploying applications: traditional deployment, virtualization, and then, of course, the start of our show, containerisation. Picture this: a time when traditional deployment methods ruled the roost. It was a simple setup where hardware, operating systems, and application coexisted on the same server. In this structure, deploying an application was like putting together a complex puzzle. Developers had to meticulously configure the server environments, ensuring that it matched the specifications of the application. Since different applications shared the same server, that led to potential conflicts with various dependencies, libraries, and configurations that had to be managed. Once the application was ready, developers had to pass on the detailed documentation and instructions to the operations team. This documentation included information on the server environments, required dependencies, and step-by-step deployment procedures, which of course required manual intervention. Managing different environments was a daunting task that resulted in a tightly integrated but potentially messy environment. Now, the operation team took the reins. They had a task of setting up the servers, installing the necessary dependencies, and configuring the environment based on the provided documentation. As you can imagine, this process was time-consuming and prone to errors. Operation teams struggled with the challenges of maintaining consistency across different environments. The slightest deviation from the documented setup could result in unexpected behavior or failures. Debugging and troubleshooting were often tedious, requiring a deep understanding of the intricacies of both the app and the server environment. Due to isolation issues and inability to define resource boundaries for applications on our physical servers, resource allocation became a headache, leading to underutilization of resources and potentially scaling issues. Operation teams struggled to scale infrastructure efficiently. And lastly, physical servers were costly to maintain, and also they lacked flexibility, resulting in significant financial overhead. In summary, deployments were manual, time-consuming, and error-prone. Now, we are going to fast forward to the era of virtual machines, a groundbreaking innovation that radically transformed computing, offering a solution to many challenges associated with traditional deployment. Now, let's go through structure explanation in a little bit more detail. In the virtualization setup, the hardware provided the physical foundation. On top of that, the operating system served as the host for a hypervisor, a specialized software layer responsible for managing and creating virtual machines. Each virtual machine then contained its own complete operating system, application, and dependencies. Virtual machines brought about a significant evolution, providing developers with a level of isolation and operational flexibility. This also means virtual machines introduced a game-changing level of isolation for developers. They could now run multiple virtual machines on a single physical server, each containing a full copy of an operating system, the application, and all necessary binaries and libraries. The improved management of the environment facilitated more straightforward additions and updates to applications, effectively solving scalability issues. Virtualization became a key player in optimizing resource utilization, allowing for better efficiency and adaptability in dynamic computing environments. However, despite these advantages, virtual machines had their own set of challenges. They were heavyweight, consuming tens of gigabytes of space. This has not only affected storage, but also contributed to significant resource consumption. The process of spinning up virtual machines could be time-consuming, impacting the speed at which applications could be deployed and scaled. So if you're excited to learn the ropes of Docker and level up your skills, hit that subscribe button now and ring the notification bell. You won't want to miss any of our upcoming episodes. And lastly, we get into the current age of containers and Docker. The deployment process has undergone a revolutionary change. Now let's take a look at the structure explanation of containerization. In the containerization paradigm, the hardware remains the foundation and the operating system continues to play a crucial role. However, instead of a hypervisor and virtual machines, we introduce a container runtime. The container runtime is the magic ingredient. It allows the deployment and execution of containers directly on the host operating system, eliminating the need for a hypervisor and the overhead of virtual machines. Containers are a type of virtual operating system that provides a self-contained environment for running applications. Essentially, the operating system itself is virtualized, and this abstraction at the operating system layer enables the packaging of code and dependencies into a standardized software unit. Containers are designed to share the host operating system's kernel, making them more lightweight and efficient than virtual machines. This streamlined architecture simplifies the deployment process, resulting in a faster, more resource-efficient, and agile system. But of course, with innovation comes challenges. Security concerns arise due to the shared kernel in containers, needing collaboration between developers and operations teams to fortify security practices. Now, let's talk about Docker. Docker is a tool designed to make your life as a developer or system administrator easier. With Docker, developers package their application and its dependencies into a container. Docker effectively eliminates the need for developers to worry about the intricacies of the underlying infrastructure. Development teams are now entrusted with the task of not only crafting application code, but also encapsulating it within containerized environments. This involves specifying dependencies, configuring runtime settings, and addressing networking aspects to ensure seamless deployment and operation. Developers play a crucial role in optimizing applications for containerization, facilitating smoother collaboration with operations teams. Operations teams are tasked with overseeing the configuration, deployments, and maintenance of the containerized environment. This includes ensuring the proper functioning of containers across various stages, from development all the way to the production. This is a game changer because it puts an end to the classic "it works on my machine" headaches. Container orchestration platforms, such as Kubernetes, have become central to scaling, load balancing, and ensuring high availability. Operations teams are responsible for optimizing resource utilization, monitoring performance, addressing security concerns, and guaranteeing the seamless operation of containerized applications. Containerisation is not a replacement for virtualization, but often complements it. Modern infrastructure often combines both virtual machines and containers to leverage the strengths of each other. This shift emphasizes the need for operational excellence and collaboration with development teams to achieve a harmonious and efficient software delivery pipeline. Containerisation emphasizes the need for a strong DevOps culture. The adoption of containerisation has underscored the importance of fostering a strong DevOps culture. Teams need to break down silos, collaborate in real time, and share responsibilities. Automation, particularly through continuous integration and continuous delivery pipelines, has become integral to the deployment process, emphasizing the need for a seamless integration of development and operations practices. In its early days, Docker was primarily designed for Linux environments. Running Docker on Windows directly, well, that seemed like a distant dream. But as the demand for cross-platform compatibility grew louder, a hero emerged: Docker Desktop. Docker Desktop, as we know it today, has played a pivotal role in breaking down barriers that once limited Docker's reach. Windows or macOS, it doesn't really matter. Developers can now harness the power of Docker without the headaches of complex workarounds. This isn't just about compatibility anymore, it's about empowerment. Docker Desktop has given developers the tools to focus on what truly matters, and that is building innovative and reliable applications. That wraps up our exploration into the fascinating world of containers and Docker today. In our next episode, we'll take the practical step of installing Docker on your local machine. Once again, thanks for joining us. To make sure you don't miss out on this hands-on tutorial, hit that like button and of course subscribe for more exciting content. And lastly, join our Medium blogs for insightful articles and tutorials, as well as our vibrant Discord community to connect with like-minded people and learn even more. The links can be found in the description below.